Hello, and welcome to this introduction to SAP HANA Advanced Analytics. My name is Vitaly Rudnitsky. I'm one of SAP Developer Advocates. In this series of videos, together with my colleagues from SAP Engineering team, we will bring you into the world of SAP HANA Advanced Analytics in general and multimodal capabilities in particular. So let's roll. Let's first look at the history of databases and introduce some context. File systems and navigational databases were used by computer systems to persist their data, including first SAP applications as the company was established in 1972. The SQL programming language was first developed in the 1970s by IBM. This programming language was created following the publishing of Edgar F. Todd's paper describing a relational model of data. And then, since the 1980s, relational database management systems, or DBMSs, have been a common option for the storage of information in databases used for financial records, manufacturing, logistical information, personal data, and other business applications. Relational databases have often replaced these legacy navigational databases because RDBMS were easier to implement and operate. And so by 1986, ANSI and ISO standard groups officially adopted the standard SQL language definition. The growing volumes of data in business applications and the rising popularity of business intelligence, which demanded complex analytical and ad hoc queries without impacting business transactions, introduced the approach of splitting business systems into separate OLTP, or online transactional processing, and OLAP, or online analytical processing. In the 1990s as well, in the attempt to address the so-called object-relational impedance mismatch between relational databases and object-oriented application programs, OODBMSs were introduced, or object-oriented database management systems. Although they didn't gain the popularity as wide as RDBMS, it was a strong signal that the relational model was not one size fits all. Traditionally, the relational database model used in business systems mainly processed simple numbers or alphanumeric data types like product number, description, invoice number, amounts on this invoice. But by the end of this 20th century, the rapid growth of geographic information systems, or GISs, demanded standardization of geospatial data processing, including databases. And so in 1999, OpenGIS Consortium published simple feature specification for SQL, or basically how spatial data should be stored and processed using SQL. And with that, we are entering 21st century. This was the time when I was a BW consultant myself, and I still remember these glorious years when the customers who have ERP systems larger than terabyte would be joining this elite terabyte club. Who would think that it sounds like tera years ago? But terabytes were just the beginning. The web scale brought the new requirement for data storage, and we are talking about petabytes and more in this case, and not only structured but as well unstructured or semi-structured data. Social media created the need to process connected data and therefore processing graph data. With mobiles, we know that we need to deliver this data fast, and in-memory processing went mainstream. All of these new requirements, be this processing huge amounts of data or processing semi-structured data or processing graph data, created the new market that is often called NoSQL. In recent decade, we saw as well the explosion of popularity in the area of Internet of Things, or IoT. And this brought, for example, the requirement to process time series data. So where are we going now in this next decade? 2018, Forrester Consulting conducted a study among big US companies and found that even though structured relational data is still the majority of data being processed, the use of other types of data formats is on the rise. This is what they and the rest of industry are calling processing multimodal data. As well, if we look at the rise of the translytical data platforms, where translytical means processing transactional and analytical workloads in a single database, The part of this requirement from translytical workloads is that this product should be able to do advanced analytics as well. So if we look at SAP HANA, you can see that one of the main blocks of capabilities is exactly what we call advanced analytical processing, be this processing spatial or graph data or series data or semi-structured data on top of the relational data that is being stored in SAP HANA by our customers. Let's move to some demos now. So for our demos, I'm going to use the free trial version of SAP HANA Cloud. I am logged already in the trial account on SAP Cloud Platform, and I have the instance of SAP HANA Cloud already created. And from here, I can go and open it in SAP HANA Database Explorer, which I already did. And the first demo will be based on the challenge that I got some time ago from one of our SAP community members when he asked, can HANA process the location data coming from one of the map services? And this map service, which is extremely popular among all of us, is basically storing the location data in the background. As a user of this service, you can go and download this data. So what I've done, I already have this file downloaded. So this is location history.json. And if we look at it, then you can see that indeed this is a JSON file that stores locations, and for these locations there is a timestamp and then latitude and longitude, and there is as well an accuracy, I assume, in meters. Can HANA do something with this JSON payload? For that, I loaded this file already into the table, and I called this location history dumps. If we look at this data, then indeed it is just dump. Because we are going to process geospatial data, I'm going to use another IDE tool that is called dbeaver, and dbeaver has nice geospatial data visualization. SAP HANA is one of the databases that can be connected to using JDBC driver. So you can see I looked already at this table, and one thing you might have noticed is that I added another column, timestamp, where I would like to store the last timestamp recorded in location history. To be able to get this timestamp from our JSON payload, I need this select statement. This select statement allows me to read the JSON table from this column, and then I can specify the JSON path, and I can parse values in this JSON to turn them into the column. So if I would just execute this query, then this is the timestamp. It's been just a few days ago when I downloaded this location history file, and now what I want to do is that I want to update the timestamp column. Once it is executed, I can just re-execute the read. Now I have a table which has two columns. This is the latest timestamp of any recorded location. This is the just one cell or one record that stores this whole JSON payload, 17 megabytes. What I want to do in the next step is that I want to parse this semi-structured data into more columns. Therefore, I'm creating a new table. And once again, I'm going to use HANA SQL capability to read semi-structured data using JSON SQL extension and parse data like latitude, longitude, timestamp, and altitude into separate columns. So let me just execute this statement, and once it is executed, I can find this table and let me just read the content. So you can see that now we parsed timestamp into the timestamp that is readable for us, and every location that has been recorded is now stored as so-called geospatial point. Now, what can we do with this data? Let's query this. The very first query should return all the points recorded in August of this year. I aggregated all these points so that you can see that the data that is being returned is only one record, and this one record stores the multi-point spatial data type. If I want to visualize this, and this is the advantage that is coming from dbeaver, I can see all the points where I was during previous months. As you can see, this application is not recording all the time. So there were times maybe I had my mobile phone off, or maybe it just didn't record my points during these times, but there are some gaps, obvious gaps, as I was moving around. But presenting data with that many points is not that usual. So quite often we are using different kind of spatial aggregations to reduce the busyness of what we can see. Let me do the aggregation that is called envelopes. I've been in that many places, except of one place that looks a little bit strange, this one in Africa, because frankly speaking, I do not recall being there during the period during which this data has been collected. So what is this cluster in Africa? To check it, I loaded another data set which contains the shapes of continents, and it has been provided on GitHub as demo data sets from ArcGIS. So let me just show you that if I select the continent Africa, then indeed this is the data returned. Or if I would like to try the same for Europe, this is the one. But in my case, I want to find points, or what were these points that the system collected for Africa. I'm joining these two tables, my location history and the continents shapes provided by ArcGIS. And I'm using here spatial predicate, where I'm telling, find me all these points from my location history that are covered by the shape that is defined by the Africa continent. So let's execute it. It will take a couple of seconds. As you can see, it's been only 1 point August 17 last year. And even just looking at the coordinates of this point, we can see that it said that latitude was 0 degrees. So obviously there was something wrong, either recorded by my phone connecting to the satellite at this specific time, or when this data was persisted in the backend service. Because if we look and try to reproduce the route to Africa during that specific date, so what I'm doing here is that I do the string aggregation, and I'm building from these points the path that would be ordered by the timestamp for this particular day. So this is the line string, and now if I will visualize, then you can see that I would say it is impossible that I would be walking at that day here in nearby mountains in the town of Międzygórze, and then for 1 second I was just transferred to Africa and transferred back. Maybe it is possible with the modern technology, but I do not recall this happening to me. I will just clean this one particular point from my location history, and now as it was executed, and I will just try to reproduce the route that I did on this date now it looks normal, right? So I was just walking in this town of Międzygórze back and forth. Yeah, we just can go back for a second and we can just try to recreate these spatial aggregations in the form of grid. This one point in Africa is gone, and this is the aggregation of spatial location that I used to be over the last 7 years. But there are more types or more ways to do the spatial aggregations, and one of the popular ones is k-means. Let me run this. I asked HANA to cluster all the points where I was during this summer. Yes, I was on vacations in eastern Poland. I was on vacations in northern western corner of Poland, and twice I was in our voivodeship, one in so-called Klocko region and the other one in Karkonosze. So far, it looks like this all makes sense. The other popular aggregation is hexagons. So let us execute this query. Now, hexagon, let's have a look at the result. So in this case, you can see that I did the join of my location points once again with the continents, and I asked to aggregate points where I used to be in North America. Basically, I was traveling to either Sapphire Now conference in Orlando or to TechEd in Las Vegas. Usually I would travel via San Francisco just to visit our SAP Silicon Valley office on the way. Plus, I used to be on ASAC BI conference in Fort Worth in Texas, at SAP Insider Conference, and at ASAC chapter meeting last year doing as well SAP Code. To summarize, we were looking how HANA can deal with semi-structured data or JSON, and how we can do some simple queries using spatial extension in SQL in HANA. In our second demo, we will look at processing connected data. I have already my HANA Cloud trial open, and I am already in Database Explorer. We will look at the data set provided via Kaggle. This is the Marvel Universe social network. Basically, it has two files that we are going to work with. One is the nodes, and these nodes are heroes that appeared in Marvel comics or movies, and the hero network dataset that describes which of two heroes met each other in the past or have been connected to each other. I loaded this already into Marvel schema. I needed to do some data quality checks and cleanups. So there are a few tables, but the final two that we are going to look at are nodes heroes. This is a table that has all the Marvel heroes, and the network, the table that describes who of them are connected. If we look at the node heroes table, what was surprise for me, how many heroes are there? More than 6,000. And then the network, as I mentioned, describes that hero 1 met hero 2. For tables like this, HANA allows to create something that is called graph workspace. Graphs in HANA are powerful abstraction that can be used to model different kinds of networks and linked data. In SAP HANA, a graph is a set of vertices and set of edges. Both vertices and edges are represented by underlying relational table, and I just showed you two tables like this. Now, once we have these two tables, we can create this SAP HANA abstraction that is called graph workspace. As you can see from the definition, I'm telling HANA to create the graph workspace that is going to be called Marvel social net. And then for vertices, it is using the table nodes heroes. And for edges or connections between nodes, it is going to use table Marvel network. So let's run this. Now we can find a new artifact under Graph Workspace that is called social net. And this social net is exactly what we defined in the SQL, the definition of the edge table and the definition of the vertex table. Now, Database Explorer offers a preview of such a graph. I would like to mention that this preview is not something that is business user related. This is really the preview that you as a developer can use during your development. So as you can see, we loaded some subset of the nodes from the Graph Workspace and the connections for these nodes already being displayed. So one thing you might notice, for example, here for the connection between these two nodes is that it has two connections. This is because HANA Graph is always directed if two nodes are connected, we need to define in which direction or in both, like, for example, here. This is the graph that follows more of the, let's say, Twitter approach, where the fact that node A or user A follows user B doesn't mean that automatically user B follows user A. Quite the opposite to what we would call LinkedIn model, where if two users are connected, then basically both of them are connected in both directions. Now that we have our graph workspace, let's do something with this data. One usual way to work with graph data is to look for patterns. SAP HANA Graph allows you to use OpenCipher language directly in SQL. OpenCipher is a declarative graph query language developed by the OpenCipher implementers group. So the very same way as we were looking at the number of nodes in this SQL query, let's do something similar, but now using OpenCipher. So OpenCipher table is a relational table that can be returned from the graph workspace. And in our case, this is Marvel social net. And then we want to define this OpenCipher query. And the syntax of this is that we are looking in the graph to match, in this case, a node. And we want to return the hero name visible to HANA SQL as the column hero name. Let's execute it. Okay, I did a typo. Now we queried all the hero names, but we just wanted to do the basic count. Just to see that in this case, no matter if we are using plain SQL at the relational table or if we are using OpenCipher, we are getting the same count. Okay, let's now do something more complex. In our first query, we were looking only at querying the node. Now, let us have a look at all the heroes that author is following. So in this case, we got count. Obviously, if we would use just a star here, we would get all the names. The reason why I wanted to run this query is just to compare if we would do something similar, but just counting from the underlying tables. In our case, we need to do the join between Marvel network and Marvel nodes heroes, where the node is matching the hero from the network and the hero name Thor. We got the same 895 records. I wanted to use some simple queries just to build as well your trust that the results that we are getting querying Graph Workspace and querying directly relational tables are exactly the same. Let's do something even more complex. So let's try to find all the heroes who are not connected directly, but separated by one intermediate node. For this, we need to introduce the match of the pattern. And now we are saying that we are looking only at these 2 degrees of separation. So let's execute this statement. And now we are getting more than 1000 rows. So let's just do the count. So there are 90,000. And if we would like to write now the same using regular SQL, we need to start joining more tables. So instead of just one network table, we would need to join now 2 of them, and we would need additional join. Okay. So the results are the same. You can see the pattern. As more we traverse our graph, we would need to start introducing more and more joins in our regular SQL statements, and that these SQL statements would start becoming more and more complex. While using OpenCipher, it still remains quite a simple and straightforward readable query. I promise we will get back to graph processing in our next demo, but while we are using Marvel Universe dataset, I would like to shift gears and switch to predictive analytics. So when we are thinking about predictive algorithms, usually we are thinking about all these well-known algorithms like clustering, classification, regression, and so on, but little known that among more than 100 different algorithms that are implemented inside of SAP HANA, there is as well social network analysis. While we are looking at the social network of Marvel heroes, we can try to find who would be the next most probable hero for Thor to meet. Link prediction algorithm is one that we are going to use for that. And let me go back to Database Explorer. Unfortunately, PAL is not yet available for users of trial edition of SAP HANA Cloud. So for that, I need to switch to my HANA Express, where I have the same tables already loaded. Okay, so the algorithm requires that we have 3 tables. One is the table with data as an input, another one is parameters of the algorithm, and the result is the third table. So let's first create the view, which will represent the input data. You can see that this is a view directly on the relational table. And then we create the second required table, which stores the parameter of the algorithm. And in our case, we are going to use method number 1. So this is common neighbors method, and we are going to set some minimum score below which results will not be included into the result table. And here is our result table with all these objects created and populated where required. We can execute the prediction algorithm. Let's have a look. So it took about 1 minute to execute, and now we can query the results to find who is the most probable hero for Thor to meet. So according to this algorithm, Forge, I just would like to remind that the dataset that we used here is already 4 years old. So maybe in the meantime, Forge already met Thor. I promise that we will get back to graph processing in SAP HANA. In our first demo, we used OpenCipher, which is declarative graph query language, to do the pattern matching. Now, in this demo, we are going to look at GraphScript, which is an imperative programming language that provides application developers with a high-level interface for accessing and processing the graph data defined by Graph Workspace. As a demo, we are going to use Knight's Tour problem. This is the challenge that I asked participants of my workshop during SAP TechEd 2018 to tackle using SAP HANA graph processing. And one of them, Sherban Petrescu, provided his solution. Back to SAP HANA Cloud trial, I have a schema that is called Knight. And again, here we have 2 tables. One table which defines the nodes of our graph. And as you can expect, these are 64 fields of the chessboard. The second table defines the edges, and these are all possible moves where knight can jump. For such defined tables, we can now build the graph workspace. And as you can expect, this graph workspace defines that, for example, from A1, there are 2 outgoing edges and 2 incoming. So from A1, for example, knight can jump to B3 or can jump to C2. And then C2 has 6 outgoing edges and obviously 6 incoming edges, and so on. Once we have the graph workspace, we can define a procedure that defines graph processing while reading SQL data. And then the whole procedure is how to visit the whole chessboard and visit every place once. So let's run this. And let's start from the field A2. As you can see, this procedure generated 64 movements So basically visiting every field on the chessboard, starting from A2, going to C1, B3, and so on and so forth, ending on E1. This was possible thanks to the graph workspace abstract on top of the relational data and using SQL but with graph extension in SAP HANA. This concludes the demos part from my side. As I mentioned, I use publicly available free editions of SAP HANA Database, SAP HANA Cloud, available in SAP Cloud Platform Trial, and SAP HANA Express Edition, available for deployments on-prem. To find more, please visit the SAP HANA page at our SAP Developer Center at developers.sap.com. Thank you. I hope you found this short overview of advanced analytics with SAP HANA informative and entertaining, and that you will join in-depth SAP HANA multimodal sessions presented by the engineering team in the next videos of this series.